All right, guys, we just have a few other things to talk about the exponential models. And really, we looked at population growth, and where, we have this assumption that these populations can grow and it's unlimited. And that those we looked at like population of Wyoming. You can talk about your money, right? Investing money. I guess it can grow to be unlimited, hypothetically, depending on how long you have it in there. But there's also this idea of a limited population model. So I'm just going to do an example with it. These don't really follow one specific form. So that's why this is more just an example of something that has a limit to it. And I really like kind of these examples because I just think they're kind of interesting. So let's say that, for example, a lake is stopped, and we'll kind of look at kind of what this looks like. Stocked with 640 fish of some new variety or something. Okay, it doesn't really matter. So here's the thing. I'm not going to write this in the example, but you can write it if you want. So why is this a limited population? Because the size of the lake, the availability of the food, and the number of like other fish, right? So maybe this 640 are like trout, and then there are other fish. I'm not a fisherwoman, bass, maybe something like that. But the conditions, okay, we'll just say, whoa, look at what I just did over there, you guys. That was crazy. The conditions of the lake are such that, I don't know if that grammatically is correct, but I'm going to just go with it, are such that the number of other fish, not the number of other fish, sorry, such that this type of fish, that's what I meant to say, excuse me, English. Has a limiting value. So when I say limiting value, I mean pretty much, this is, again, it's a mathematical model, right? So remember, mathematical models, they take the real world, and mathematical models try to describe that real world with mathematics. Remember, mathematics is everything that is pure and true and right in the world, and the world isn't perfect. I call it pure math world. I like to live in pure math world a lot. But we just estimate, this mathematical model is going to estimate, and based on information, right, that the limiting value of this type of fish is going to be 3,040. Okay, so then we're given this function. Then the population of these fish, let's say, I hope that's pretty obvious, after T months is given by. So here's the function. So right now I'm not giving you like a form for it or anything. I'm just going to give you the function. P of t equals 3,040. So that's where that kind of number comes into the function. And then what happens here when we have a limiting function, again, this population can't grow exponentially now. Well, it grows, I guess, exponentially, but not in the sense that everyone thinks what that means, right? So this is e to the negative 0.32t, okay? And if you look at the graph of this, so if you think about what happens here, let's just kind of consider maybe what happens here as t gets really, really, really big. Remember, this guy is negative, right? So this really, if you think about this part of the graph, this is really 3.75 over e to the 0.32t. So look at what happens as t gets really, really, really big. As t gets really, really big, this denominator here is getting huge. And so you're taking a relatively small number like 3.75 and you're dividing it by really, really big numbers, like a million, like I was going to say 1,000, a million, let's get bigger than a million, 2 million, right? You're dividing it by really, really big numbers. So this guy right here is going to get really, 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 really small. So as t goes to infinity, okay, this guy is going to 0. So what we see is that we get then this horizontal asymptote that the function is going to get closer and closer and closer to. Technically never is going to hit it, and I know that's kind of weird to think about when you're thinking about number of fish. Technically never going to hit it, but what the graph, it depends on kind of what the graph of this looks like. If I let t be 0, I get 30/40 divided by, 1 plus 3.75, so I get about a fourth of that. And so what happens is, and this might not be the perfect graph of it, sometimes it kind of goes like this and then comes up like that. But you can see this still kind of grows exponentially, but not in the way that we would think of, right? An exponential function growing. Still growing, but it has a limited value in its population. Another example of this is like if you had an epidemic of some disease in a population, right? And you had maybe a function that told you the number of people that were infected with that disease. There's a finite number of people infected with that disease, so that function isn't going to go to infinity. We could even talk about the zombie, apocalypse or something someday. That's a happy thought. So let's just do a couple of things. Find the population. This is going to be pretty simple. Find the population of the fish. At 0, 5, and 20 months. Okay, so I'm not gonna belabor this point too much. I'm sure you can plug in numbers, but let's just kind of look at some of the numbers and what's happening here. So we're gonna go ahead and plug in obviously p of 0, right? If I plug that in, I'm gonna get that 340 divided by 1 plus e to the 0 is 1, 3.75. So I get that 340 divided by 4.75. And what do you know? This should make sense, you guys. Why is it 640? Because we said that was our initial amount, right? That we stocked those fish. So these are pretty easy. You can put in p of 5, right? Just be careful how you put this in. So 5 times a negative 0.32. And then you raise e to it. If I'm using my iPhone calculator right now, so it's very important that you do this in order. So I actually did the denominator, and then I'm going to take 1 over that in my calculator and multiply by 30/40. So I get 1,730. Now think about your answer, right? Does that make sense? Well, it's bigger than the 640. It's less than the 340. So I think that's reasonable. What would we expect when we put in 20? We would expect, right, that we're going to get closer and closer to that 340. And so I'm going to go ahead and do that. Times 3.75 plus 1. And the interesting thing here is that denominator is going to get closer and closer and closer to 1, because that will get me closer and closer to 340. And we get, 3,021.2 basically. So you want to get closer to 340, you just got to go further out in time, and then that's the restricting or limiting your population. I hope that kind of makes sense. All right, so the last thing I want to talk about in this section is one of my favorite things. I don't know why, but I just think it's fun to talk about. I know that sounds weird that talking about decay is fun, but what if we don't have a growth, right? So we talked about a limiting growth. We talked about an exponential growth where it can grow as fast as we really want it to. But what about if we actually have a population decline? And one of the things that we're going to kind of focus on is decay. All right, so this is what we call exponential decay. And this will be our last example for this section. So exponential decay. So here's what I'm just going to give you the function for this. It's going to be very, very similar to the function we already saw for exponential growth, but now I have a negative kt where k is still greater than 0. Now, why is k greater than 0? Because I want this to stay negative. If k was negative, this would be positive. Let's think about what this function is doing. So our original exponential growth, right? This is p naught e to the kt where k is positive. What happens when I take this function and I put a negative right now there. Remember what that does, you guys. It actually, right, flips it across the y-axis. So if you notice, I am getting a decay. Couple things here, that P naught is still the initial population. That K right there is just called our decay constant. Okay, written, if it's given as a percentage, then you need to write it as a decimal. Okay, so that that is kind of a yeah, I don't know what else to say about that. All right, so the thing that I want to talk about the most on here is carbon dating, because I just think it's such an interesting thing, right? So you've probably heard of carbon-14 dating. What it basically does is it measures the amount of radioactivity in anything that was living, and it takes its half-life, right? So a half-life of a substance is basically the amount of time that it takes, right, for a substance to lose half of its radioactive material. So for example, like the half-life of bismuth, that's the example your book gives you, is 5 days. And what that means is that half of, like, however much bismuth I have that is radioactive, half of it will be gone in 5 days. Okay, so that's what we mean by a half-life. And that's going to be the important part here, because when we look at half-lives, they actually will, you'll see they decay exponentially. So like, let's kind of look at this. Let's say I have P naught here, and after, 5 days, let's talk about bismuth here or whatever, I'm going to have half of that after 5 days. So here I'm at P naught, and then after 5 days, I'm going to be at half. And then you guys, because the half-life is 5 days, after another 5 days, so I'm at 10 days now, I'm going to have half of what I had originally, right? So I'm going to have half of that. And then after another 5 days, you see a pattern here, because that's what math is. After another 5 days, I'm going to have half of whatever I had before. So that's what I had at 10, so I'm going to have half of that. Right? Do you see how this is exponential? So if you kind of look at the graph of this, this is an exponential. Oh, sorry, that's so squiggly. This is an exponential function, kind of just like we had up here. So it's a really cool kind of thing to see. And then again, if I went to 20 days, what would I have? I'd have half of the remaining, and that's exactly what a half-life is. So now, again, you can memorize the formula for decay rate and half-life. You are welcome to do that. Again, it involves the natural log of 2 and a t, or you can actually just kind of figure it out, which is my preferred method, based on the information that you're given. So let's go ahead and do an example of this. I want to maybe do 2 examples of this, because these are just a good time. Okay, so I'm not going to write down all of this, but I'm just grabbing this example from your book, one of the exercises in your book that I thought was kind of cool. So in February 2006, in the Valley of the Kings in Egypt, a team of archaeologists uncovered the first tomb since King Tut's tomb had been found in 1922. Okay, so the tomb contained 5 wooden sarcophagi that contained mummies. Oh, those mummies exhibits are crazy. My husband and I just went to one in Chicago at the Field Museum. The archaeologists believe that the mummies are from the 18th dynasty, around 3,300 to 3,500 years ago. So interesting, okay? So determine the amount of carbon-14 that the mummies have lost. So we need a couple of things here, okay? So first off, let me tell you a little bit something about carbon-14. So carbon-14 has a half-life of 5,050 years. So carbon-14 has a half-life, and this is something I would give you, but you'll probably end up memorizing it, even though you don't want to. You'll probably figure that out. But so remember what that means. It takes 5,750 years, right, for whatever we're dealing with to lose half of the amount in it. Okay, so what we need to do first, well, let's write down the problem first. We'll just simplify this problem basically and say that we have mummies, right, from 3,300 to 3,500 years ago. And we want to know, determine how much carbon. The mummies have lost. So this seems pretty straightforward, but we got to figure out how to kind of get our decay function. Okay, here's what we know. We know that P of t, right, is P sub 0 e to the negative kt. And you might be worried. You might be like, Sarah, but I don't know the initial amount of carbon that was in the mummy. That's okay. You don't need to know that, right? We'll just talk about this maybe as a percentage, okay? So determine the amount of carbon-14 that the mummies have lost. Well, what I need to find is I need to find the half-life. So here's how we're going to use the half-life. I know, right, that when t is 5750, after 5,750 years, the initial amount of carbon, so this is my initial amount of carbon, right, carbon-14. I think I can write it like that, carbon-14. I don't know. If not, I apologize to all the chemistry teachers out there. So look at what, can I solve this equation? I sure can. Look at, I know that after 5,750 years, I'm going to have half that initial amount of carbon. So let's divide both sides by the P naught. Look at that. That was easy to do, right? So now I have e to the negative 5750k equals 1/2. And now I'm just going to ln both sides like we know we should. And again, you can see this is going to happen every time you use a half-life, right? Because you're going to get half that original. So you are welcome to memorize that formula if you want to. I don't like memorizing formulas, you guys, because I never trust myself. Natural log of 1/2. Now, the formula is going to be a little bit different because what the formula does is it takes the natural log of the top minus the natural log of the bottom, and the natural log of 1 is 0. So anyway, but you're welcome to memorize that formula. Just make sure you memorize it correctly. That's why if I can, I don't like to memorize formulas and I like to think it through instead. All right, so 0.5, natural log of that, divided by the 5750. And we get k to be 0.000121. Okay, so that's my decay constant, and that's going to be true for carbon-14 no matter what, right? Because we didn't even talk about what we had there. There are other examples like the half-life of the bismuth or whatever, and we could talk about half-lives of other things too. It doesn't have to be radioactive material. This is probably just, the thing that you've heard of the most. So what does this function give me? It gives me the amount of carbon-14 in 0.000121 T. My initial amount was P naught, right? Don't know how much that is, but it's going to give me however much after T years. And so what we need to know, right, is how much is going to be left 3,300 to 3,500 years ago. So let's just do 3,300 and see kind of what happens. And this is probably going to be not probably, it is going to be kind of a percentage of whatever my initial amount was. Okay, so again, it wants to know how much is left. So let's see what we got here. So remember, P naught's the initial amount of carbon-14 that I have in the mummy. So I'm going to take that 0.000121, I forgot a 1 there, times the 3,300. Make sure it's negative. And then raise e to it. So what I get is 0.671 P naught. So let's think about what this means, right? If I have a 1 P naught, right, that says I have 100% of my original amount. If I have 0.5 P naught, that says I have 50% of my original amount. So what is this 0.671 P naught? This means I have 67.1% of the original amount of carbon, okay? So what did the question ask? Determine how much carbon the mummies have lost. So if I have 67.1% remaining, right, how much am I going to actually have left? Or I'm sorry, how much have I actually lost? So how much have we lost? We've actually lost 32.9% of the original amount of carbon. Okay, does that make sense? Which makes sense, right? So I want you to think a little bit. I know I always ask you to think. I know. But remember, does it make sense that I've only lost 32%? Remember, the half-life of this sucker is 5,750 years. So I would expect to have 50% as after 5,750 years. We're just looking at about 3,300 years. We could put in the 3,500 also and see what we get. So it makes sense that I haven't quite lost half of the carbon, right? And that would be in those mummies because it hasn't been, we haven't estimated it to be older than 5,750. Okay, so whoops, sorry it jumped like that. I didn't mean for it to do that. I want to do one more example maybe of something that isn't necessarily a half-life, because not everything has to be a half-life, right? So I want to do one more example of decay, and then we'll call it good. So this next example, again, I'm being a little lazy and grabbing some good examples from your book. But this one is about the number of farms. So the number of farms in the United States has declined continually since 1950. So we have the number of farms in 1950 was 5.6 million. And in 2008, it has decreased to 2.2 million. Okay, so assuming that this number of farms is decreasing according to an exponential decay model, right? Let's estimate the number of farms. Actually, estimate when the number of farms will only be 1 million. So this data actually is based on real data. All right, so let's look at our exponential decay model. So this is another example where you have to find your decay constant, okay? So I have P naught e to the negative kt. This is going to be very similar to kind of what we had before. What do we know? What's the information that I'm given? I'm given that P sub 0, right, is 5.6. So I'm going to just put this in millions because that's the year that I'm going to start off with. And then 58 years later, in 2008, I know it was 2.2. So if I look at that P naught, that's the same thing as my initial amount of farms. So I have 5.6 e to the negative kt. Eventually I'll get to this 1 million, but what I need to do first is I need to find my decay constant. So I get, just like we did before, 5.6 e to the negative k. After 58 years, right, I know that the number of farms is going to be down to 2.2. And now I trust you can go through and solve this. I'm going to take 2.2 divided by 5.6. Then I'm going to natural log that sucker. And then I'm going to divide by the 58. So I think we've already done that. So I think you can probably do that. So K then is equal to 0.016, let's say 11. So just like our population growth, now remember that's my K. Remember my decline has the negative in front of it. You really could use this formula for growth or decay. You just get a positive K if you have growth and a negative K if you have decline. All right, so what do I want to know? I want to know when, remember what this function does, you spit in the years after 1950, and it's going to spit out the number of farms in millions in the US. And I'm going to set this equal to just 1, not 1 million, because look at how we've described our outputs here, but I'm just going to set it equal to 1. 1 divided by 5.6, so again, same kind of thing. We'll take the natural log of that and then divide by 0.0. I did something wrong there. 1 divided by 5.6. There we go. Natural log of that. How did I know I did something wrong? Because when I took the natural log of 1 over 5.6, I did not get a negative number, which was going to be a problem when I divided by this negative number here. So again, divide by 5.6, take the natural log of both sides, and then divide by that negative 0.01611. And what do I got T to be 106.94. So I'm not assuming it's going to be in the year 106, right? I need to add 1950 to that. So this is saying it's estimated in the year 2056, well, 2057, probably 2056. We don't want to round up. That's when we're going to have only 1 million farms. All right, guys. These are really interesting problems. So if you have any questions, of course, let us know. But this should kind of get you going into, you'll kind of see the same pattern with these. I am going to assign a couple problems that aren't exactly the population growth or population decay models, but they're exponential models that I think are pretty interesting, and I hope you think they are too. See you later.